Hello folks, I am here to finish example 4 from the SEM class that describes the connection between CFA models as estimated using structural equation modeling software and the same types of models as estimated using multi-level modeling software. So I'm demonstrating these connections using SAS mixed, but you could use any multi-level modeling package that contains the options that we need. So the first step to make the connection into the multi-level modeling framework is to reshape the data. So when we're doing analyses using structural equation models, the data are in a wide format with one row per person and the variables to be analyzed in separate columns. In order to use multi-level modeling software, which is a univariate software that takes only one column as an outcome, we have to put all of the item responses into that one column. So I am importing the data from M+. I am then making a new data set and I am stacking it. So first I have to remove the missing values that I had put into the M+ file, and then this code right here is reshaping the data, or stacking it as I call it, from wide to long, in which case we have one new column that is going to be the item number, so 1 through 6 in this example, a second new column that is going to be all of the item responses, and it loops across the 6 to store each separate item response one at a time. The output option then writes a new line of data, so when this process is finished, what we would have is a new data set in which each person has 6 rows, one for each item response. So first off here, as an example, we have what the null baseline independence model would look like if it were done this way. And in the null model, it estimates all of the item means and all of the variances, but no covariances. So we accomplish that by taking the new item number index and telling SAS that it is to be treated as a categorical variable or a factor variable by putting it on the class statement. So what it's going to do then is estimate as many fixed effects as we have items. It will be parameterized as one intercept and then mean differences between each of the other items relative to a reference item. I am then using the R matrix and specifying it to have a heterogeneous diagonal. So each item is going to have a separate variance, and I'm doing that via a Toeplitz heterogeneous structure with order 1, meaning I only want the diagonal, none of the off diagonals. And so this creates this structure where there's no covariances, each item gets its own variance, and each item is going to get its own mean as well. So the solution for fixed effects then, in this case, it looks like I've reparameterized it, so we directly have the items. So that's, I forgot to mention that. I kicked out the intercept so that the 6 parameters would be the item means directly. So that just saves the algebra of having to put the means and mean differences back together again. So this is the null model. Next up is the other baseline model, the saturated model. And here the terminology is very similar. The way that I describe this model would be saturated means, so each item is still getting its own means, and the idea that all possible variances and covariances are estimated would be called unstructured. So this is the H1 saturated model, or what I would call unstructured with saturated means in a multi-level modeling context. So here we're using an R matrix that is unstructured with order 6, meaning the whole thing, a whole 6 by 6. So these are the variances and covariances across items, and these are the correlations across items in the R correlation matrix instead. So this should be the best possible model because all it's doing is representing the data directly. So you would get, if you asked for just a correlation matrix using descriptives, you would get the same answer if you have complete data. However, if you have incomplete data, these matrices would be trying to recreate the model parameters if you had complete data under an assumption of missing at random. Whereas if you had descriptives, it would be missing completely at random using only the data that you have. So this is the information that your factor model is going to be trying to reproduce, which is why it's helpful to know what it looks like in the first place. This is also then the H1 model used for the likelihood ratio test of model fit. So there's all of the separate parameters. And again, here's my 6 item means given by the model fixed effects. Next one here is showing you what the factor analysis option does in mixed. That would recreate what we had as model 1 earlier in this handout, a single factor model in which the factor variance is set to 1, the factor mean is set to 0 for identification, which means that all loadings and intercepts would be estimated as well as all error variances as usual. So SAS has this built in. Type equals FA stands for factor analysis, and the 1 means how many factors. So now what we have in the R matrix is what the factor model predicts. So this is the model estimated or model recreated variance covariance matrix, where the diagonal is a function of the true score part and the error part, and the off diagonals are the predicted covariances between the items. And here is the correlation version that would be recreated by the standardized solution. And the parameters then, as labeled in SAS, so these first terms here are the error variances for the items, and these are your factor loadings. So it's which item and then which factor. So we only have one factor, which is why the second value here is 1 in every case. And these are the same factor loadings that we got out of M plus or R in doing the exact same analysis. So type equals FA gives us a single factor model solution. So I like to make this connection because it highlights the idea. In the longitudinal class, we saw a whole bunch of other types, like you can have autoregressive or topolits, or you can throw a random intercept in there and then have the types apply to the residuals that are left. But factor analysis is another type of alternative covariance structure. It is. And it's used in a different context, but conceivably this is an option for longitudinal data as well. If you wanted to have a single factor, not have it to represent an intercept or a slope per se, but just to recreate the data. So we have our single factor model here, where each item has a separate loading, each item has a separate residual error variance, and of course each item has a separate mean, which in this case matches because of the way that we've set the factor mean to be 0. So these would be just the item means that we saw before. Here is a simpler model. So this is a tau equivalent model in which we have constrained all of the loadings equal. In the IRT unit, we will know the same type of model as a Roche model instead, but the term tau equivalent is used to describe a model in which all loadings are forced to be equal. In order to do this in SAS, I have changed the method of identification so that all of the loadings are held equal, but they're held equal at 1, so that I can estimate the factor variance instead. So we would either fix the factor variance to 1 and estimate the single constrained loading, or we would do what I have here, where in estimating the factor variance, that means we have to fix the constrained loading to 1 for identification. And the random statement here is the mechanism by which we would get our factor variance. So I'm estimating a factor variance. It is a random intercept in terms of what it would mean, because we have forced all of the loadings to be equal. And then in the R matrix, I have allowed, again, a heterogeneous diagonal only, meaning that there is a separate residual variance that's going to be estimated for each item, but no residual covariances. So the variance of the factor then is estimated in the G matrix here, and when we put the R and G back together again, we get our combined V matrix, which has different variances on the diagonal because we have different error variances per each item, but it has the same value on the off diagonal for the model implied covariance because all of the items are expected to be equally related in terms of their covariance. They're not equally correlated because of the differences in variance, but they're equally covariate. And so this highlights the tie between the multi-level version of the model notation and the SEM version of the exact same set of ideas. So the R matrix is the psi matrix in SEM, so the end of the equation where the error variances and any covariances would go. G is phi, So the variances of the factors and the covariances of the factors are in the G matrix. Z is the matrix that holds the predictors to be given random effects. In this context, it is the same thing as lambda, which is where the factor loadings would go. And so then when you put it all back together again, we have V as the model implied marginal covariance matrix, and that is the same thing as sigma in SEM or CFA notation. So it really is the same underlying technology that's doing both of these, just with a different set of notation for a different purpose. All right, last but not least, to complete the sequence, for tau equivalent, a stricter condition than that is not only equal loadings, but also equal error variances, which is a condition known as parallel items. So I have forced all the error variances equal. I have continued to force all the loadings to be equal and equal at 1 specifically so that I can estimate a factor variance instead. And I have operationalized this parallel items model in SAS as a random intercept plus a diagonal R matrix that has equal variances across the items. So type equals VC, which is what the standard R matrix is if you don't ask for anything else when you fit multi-level models. So now the error variance is forced to be the same across all 6 items. The factor variance is still here in G, and the model implied what we would call sigma in SEM class, or what I would call V in MLM class, then has a particular shape where it's equal variances on the diagonal, equal covariances on the off diagonal, which translates into equal correlations, and this is known as compound symmetry in multilevel modeling class. So a parallel items model is a compound symmetry model. All right. So I had wanted to continue and fit the 2-factor model, but it turns out that SAS doesn't let you do that in a confirmatory way. It fits the EFA version in which each item would load on each factor, which is what I don't want. So that's the end of the story with respect to tying CFA results into MLM results. If you want to go the other way, so the next video I'm about to record is for the multi-level modeling longitudinal class, in which I will describe how those models get estimated as growth curve models in SEM instead. So stay tuned for that. Thanks for being here, and we'll see you on the other side.